Hi everyone, this is Ozon, and today we're going to be talking about insulators, semiconductors, and conductors. I like starting with the simplest idea, something even a respectful elder with only grade school education could understand with no problem. Electricity moves kind of like water flowing through a pipe, so imagine three kinds of pipes. An insulator is like a pipe that is totally blocked. No matter how much water you try to push, it won't pass. That's how rubber or wood act with electricity. They keep it from flowing. A conductor is the opposite. It's like wide open pipe with smooth inside surfaces. Electricity flows through easily, just like water flowing freely through a big pipe. Metals like copper behave this way. A semiconductor is like a pipe with a valve on it. Sometimes it's closed, sometimes you can open it a little, and sometimes you can open it fully. It depends on temperature, light, or how the material is treated. This ability to sometimes block and sometimes allow electricity is exactly what lets us build computers and phones. Semiconductors respond to tiny changes in the environment, and that allows us to switch current on and off. In engineering materials, everything comes down to bonding. The three primary bonds are ionic bonds, where one atom gives up electrons and another takes them. They stick together because opposite charges attract. Covalent bonds, where atoms share electrons, silicon uses this type, which is why semiconductors behave the way they do. Metallic bonds, where electrons float freely like a sea around the atoms, giving metals their conductivity. We also have secondary bonds like van der Waals forces and hydrogen bonds, which are weaker but important in polymers, biological materials, and even things like adhesives. When many atoms come together in a solid, their electron energy levels overlap and spread into energy bands. The most important are the valence band and the conduction band. The band gap is the energy gap between them. If the gap is small or non-existent, like in metals, electrons move easily. If it's huge, like in insulators, electrons don't move at all. Semiconductors sit right in the middle. When we did our resistance lab, we physically measured how the resistance changed when we used wires of different lengths and thicknesses. The formula, as you can see in the title, summarizes exactly what we saw. L is when we made the wire longer, resistance went up because the electrons had more distance to travel and more chances to get scattered. Second one, when the wire was thicker, resistance dropped because electrons had more pathways to move through, just like having more lanes on a highway. And lastly, the resistivity is a property of the material itself. Copper has a low resistivity, silicon has a high resistivity, and rubber has such a high resistivity that it's basically an insulator. So this single equation captures both the geometry of the wire and the material's nature. Our lab was a perfect illustration of this relationship. To explain semiconductors to someone majoring in the arts of literature, I like using an everyday analogy. Think of electrons like cars driving along a highway. When an electron moves forward, it leaves behind an empty spot, like an empty parking space. We call that empty spot a hole, and it behaves like a positive charge moving backwards as electrons fill one space after another. Mobility is like the quality of the road. If the road is smooth and open, cars move easily. That's high mobility. If the road is bumpy and jammed, cars move slowly. That's low mobility. In intrinsic semiconductors like pure silicon or pure germanium, electrons and holes naturally appear from heat, and they appear in equal numbers. But in extrinsic semiconductors, where we add impurities, like adding phosphorus to increase electrons or adding boron to increase holes, the mobility and the number of carriers can change dramatically. It's like adding more cars or creating more parking spaces in one direction than the other.
How's it going, everyone? This is Nick Rychek. I'll be doing slide 5. The color of an LED is completely controlled by the semiconductor material's band gap energy. If electrons fall across a bigger band gap, they release a higher energy photon. which corresponds to a shorter wavelength. That means colors like blue or green. If the band gap is smaller, the photon has lower energy, creating a longer wavelength like red or even infrared. GAP has a longer band gap, so when electrons drop across it, they release photons in the green range. GAAS has a smaller band gap, so the photons it emits fall into the infrared region, which is invisible to the human eye. So the color isn't because of dyes or chemicals, it's purely the physics of electrons' transitions. At room temperature, silicon's electron mobility is around 1,350 centimeters squared per volt second, and hole mobility is around 480 centimeters squared per volt second. This shows electrons move much faster than holes because they're lighter and scatter less. The intrinsic carrier concentration of silicon at 300 Kelvin is about 1 times 10 to the 10 carriers per centimeters cubed, which is extremely low. To give perspective, pure water contains more ions than that. That's why pure silicon is almost an insulator. It just doesn't have many carriers. These basic values help us calculate conductivity and show why doping is essential in electronic devices. Using the formula below, we can plug in the small intrinsic values and get a conductivity that is incredibly low, far lower than any usable metal. Then, when we calculate the resistance of a 1 centimeter long, 1 millimeter squared silicon bar, we find that the resistance is extremely high. This illustrates a key idea. Pure silicon is almost useless as a conductor. It's the same material that powers our electronics, but only after we modify it with doping. These calculations really highlight the difference between intrinsic and extrinsic semiconductors.
Hey guys, Tristan Allen here. When the temperature increases, more electrons get enough energy to jump across the band gap into the conduction band. Intrinsic silicon has an exponential relationship between temperature and carrier concentration. At around 700 Kelvin, the number of carriers is so large that the material behaves much more like a conductor. This is why semiconductor devices must be carefully temperature controlled. If the temperature gets too high, the semiconductor stops behaving predictably and can even fail because too many electrons get excited. Now let's consider doping. Adding 2 times 10 to the 19th boron atoms per cubic centimeter creates a very heavily doped p-type semiconductor. Boron has one fewer valence electron than silicon, so when it comes to form bonds, it leaves behind a hole. Because the doping level is so high, the hole concentration P is approximately equal to the doping concentration Na. The electron concentration becomes extremely small because N equals Ni squared over P. This means electrons barely contribute to conduction at all. Holes dominate everything. The strong p-type behavior is what we use in making p regions of diodes and transistors. Now that we have so many holes, the conductivity is dramatically higher. Even though hole mobility is lower than electron mobility, the sheer number of carriers means that sigma increases by many orders of magnitude compared to intrinsic silicon. If we compute the resistance of the same 1 centimeter long silicon bar, we find that it becomes extremely small. It behaves more like a poor metal. At higher temperatures, two effects happen. Carrier concentration increases and mobility decreases. The increase in concentration usually wins for heavily doped silicon, so conductivity continues to increase with temperature. This shows how doping turns silicon into a controllable material for circuits. In summary, everything in this presentation connects back to one big idea: controlling how easily electrons move. Insulators, semiconductors, and conductors differ in how tightly they hold their electrons. Bonding creates the band structures that decide material properties. Temperature, doping, and material choice all modify how many electrons or holes are available and how easily they move. Finally, by adjusting the band gap, we can even choose the color of an LED or control how a transistor behaves. All of these principles are what make modern electronics possible, from phones and computers to solar panels and LEDs.